Why does anomaly detection matter in data analysis? Picture this. You're navigating through a sea of data, searching for patterns, insights, and trends that can inform your decisions or drive your AI models. But suddenly, there's a blip on the radar, an unexpected data point that doesn't fit the established pattern. That's an anomaly, and it could be a signal of something significant, or it might just be noise. But how do you tell the difference? Today, we're diving into the world of anomaly detection, exploring two powerful techniques: statistical analysis and isolation forests. Statistical analysis, a method that's been around for decades, is the old guard of anomaly detection. It relies on the assumption that data follows a particular distribution, often a Gaussian or normal distribution. If a data point falls too far from the mean, it's flagged as an anomaly. For example, if you're analyzing the heights of adult men and you encounter someone who's 12 feet tall, statistical analysis would flag this as an anomaly. However, this method has its limitations. It assumes that your data is normally distributed, which is not always the case. Real-world data can be messy, skewed, and far from normal. It's also sensitive to the scale of your data. A small anomaly in a large dataset might go unnoticed, while a large anomaly in a small dataset could skew your results. On the other hand, isolation forests, a relatively new player in the game, take a different approach. Rather than relying on assumptions about your data's distribution, they use binary decision trees to isolate anomalies. The idea is simple. Normal data points will require more splits to be isolated, while anomalies will be isolated quickly. For instance, imagine you're analyzing a forest full of oak trees, and there's one lone pine tree. An isolation forest would quickly isolate the pine tree as an anomaly, as it's distinctly different from the majority of oaks. This method is particularly effective for high-dimensional datasets, where statistical analysis might struggle. But, like all methods, isolation forests are not without their drawbacks. They can be computationally expensive, particularly for large datasets. They also tend to be more sensitive to the number of outliers in the data. A high number of outliers might cause the isolation forest to consider them as normal, leading to missed anomalies. In summary, both statistical analysis and isolation forest offer unique advantages in anomaly detection. Statistical analysis is a tried-and-true method, effective for normally distributed data and offering a simple, intuitive approach. Meanwhile, isolation forests provide a powerful alternative for high-dimensional, non-normally distributed data, although they can be more computationally demanding. Anomaly detection is a crucial part of data analysis, helping to identify significant deviations that could indicate errors, fraud, or simply interesting patterns. By understanding the strengths and limitations of different methods, you can choose the right tool for your data and make the most of your analysis. Remember, in the vast sea of data, not all anomalies are noise. Some might be the key to your next big discovery.